Okay, so in this lecture I'm going to formally define and give a few results about projective geometry. But first, I'd just like to do a little thought experiment. Imagine you are a bee inside a beehive which goes on forever. Now we're used to looking at these hexagonally tiled beehives from above, but instead imagine you're actually standing on such a thing. What would you see? Thinking about this kind of construction is very close to the heart of projective geometry. So later on I'm going to talk about how we can produce this construction using only straight lines, no compass or anything like that. We can produce basically a bee's eye view of an infinite beehive. But first, let's get down to the history and definitions. So here you are, straight from Wikipedia. Projective geometry is the study of geometric properties that are invariant under projective transformations. Okay, so I think the easiest way for most folk to get their head around what projective geometry is about is to think about perspective art. So, for example, imagine you're an artist who's been contracted to draw a picture of these railroad lines. Let's presume that the trains aren't running, so you've got plenty of time. And so you can set up your canvas, which maybe is sort of slightly see-through, and you can set up your eye and get your marker, and then you can just mark on the canvas all the different shapes that you can see through this semi-transparent canvas. So as you can see on the right, there's a kind of mathematical model of this. The canvas is called the picture plane. That red ball labeled C, that would be like the artist's eye. And these lines L1 and L2, they would correspond to these railroad track lines disappearing away from the artist. So the artist sketches these lines as they are projected onto this semi-transparent canvas. So essentially they're just sort of tracing the places where the photons are coming from the railroad tracks through the canvas into the artist's eye. And as you can see from the picture, well, from both pictures, we have this interesting matter that these railroad tracks appear to actually be converging towards each other in the 2D picture. Now, of course, in 3D, if you go along the railroad tracks, you find that they never actually meet each other, hopefully. But from the perspective of this 2D picture, they do look like they're meeting on the horizon. And although that might just seem like a kind of optical illusion, there's actually some deeper lessons here. So this is how a lot of projective geometry became well known during the Renaissance, when people discovered how to do perspective art, and they learnt about these notions of how you can draw something on a canvas so that it looks like it would if you were actually staring at it. The way to project 3D objects onto a 2D screen. But actually, projective geometry really started quite a lot longer ago. Perhaps the father of projective geometry was Pappus, who lived in about 300 AD. He was a fantastic Greek geometer, and he came up with one of the foundational theorems of the subject. I mean, of course, it gets difficult to know what happened in history as one goes further and further back, but we do know that Pappus did a lot of very interesting thinking about projective geometry and came up with one of the most foundational results called Pappus's hexagon theorem, which we shall explain later. It's actually kind of illustrated on the right here. So perhaps the person who blew the embers of projective geometry into a real sustainable flame was this man here, Gerard Desargues. And he was a Frenchman who lived around the same time as Descartes, and he was also very interested in geometry. But whereas Descartes had one take on geometry, which ended up becoming very popular, as I shall discuss later, Gerard had a different take on it, which was simpler, more fundamental, and ultimately not quite as well known, at least in the current day. And that was basically projective geometry. So at this time, people were starting to think about perspective drawing. They were starting to think about how you can represent these different 3D objects as 2D pictures. And also, they were starting to think about the mathematics behind that. And what's interesting is that for a long, long time before Desargues, Euclid had really been the sort of, well, perhaps I shouldn't say god, but for want of a better word, the kind of god of geometry. I mean, Euclid wrote down the stone tablets and people followed the rules. But there were some people who questioned some of Euclid's ideas, and rightly so. And basically, in Euclidean geometry, it's all about what you can construct when you have a straight edge, so you can draw lines, and a compass, so you can draw circles. But Desargues had this fascinating idea about, what about if you just consider what you can only do with a straight edge? No compass. What shapes can you create using only a straight edge? This was one of his most profound ideas, in my opinion. I think that many great leaps in mathematics come from disregarding certain details. I mean, when you're no longer allowed to use a compass, ideas of being able to measure angles, distances, symmetries, they sort of fade away. And what you're left with is something more fundamental. And so if you can prove things that hold for straight edge constructions, then they're going to be more fundamental facts. And so if you happen to be living in a universe with a certain geometry where, you know, compasses are wonky for some reason, well, you can still rely on these results that people proved only using a straight edge. This is the basic idea. It's more fundamental. And Desargues studied this meticulously, and he noted the links with perspective art, perspective drawing, and he proved one of the foundational theorems of this subject. So in order to see the contrast between Euclid's approach and Desargues' approach towards geometry, let's have a look at a famous construction of Euclid. How Euclid constructs a regular hexagon. This is a very nice idea. So we start with a compass and we draw a circle, and then we set the compass to the same radius, and then we basically just copy that around. So we have to find these intersection points. And there we have it. So this is basically how Euclid makes a regular hexagon. Very nice idea. Just using a straight edge and a compass. So now let's have a look at the sort of projective geometry version of elegant hexagon drawing. So we start off with this line, which we shall call the vanishing line. Some people call it the horizon, but I think at this point it's probably best not to get too wrapped up in physical interpretations. Anyway, we have this vanishing line and we draw 3 points on it, however we like. And we draw one line coming off each of those 3 points, however we like. And this is our sort of optional setup at the beginning. And after that, we follow some basic rules and generate a hexagon in a very interesting way. So notice we're only using a straight edge here. We're not using a compass or anything like that. So I'm using Geogebra now. I'm going to find the intersection points because these 3 lines I've just drawn have created a triangle. So here we are, we're starting off with a triangle. Now what? Well, what we're going to do next is to draw some extra lines from these 3 points back to the points on the vanishing line. So notice that each point on the triangle can be linked to one new point on the vanishing line. So that's what we do. And this creates some new points of intersection as well. And they're going to be useful for us in our constructions. Now the idea behind this whole construction is that eventually we're going to have it so that there's going to be 3 lines, 3 pink or red rays if you like, coming out of each of these lines that was on the vanishing point. So we're going to draw some more lines from these vanishing points going through newly created points in the system. So for example, there's a newly created point, we'll link it to the vanishing point D. And we can do the same thing with the other newly created points. So you can see that now points D and E, they're points on the vanishing line which now have 3 of these kind of, well, I shall call them rays. These lines which are not on the vanishing line. They have 3 rays going through them each. So they're kind of done with now. We want to draw an extra ray through C as well. So we've just drawn some extra rays. They're black at the moment. And those rays define some new intersection points. And we use one of those new intersection points to link to that leftmost vanishing point. And so now basically we've got enough stuff to make our hexagon. Let's just draw in our hexagon. So the hexagon that we're going to draw in, notice that there are these points where these rays intersect. And some points have this property that only 2 rays intersect there. And some points have this property that 3 rays intersect there. And it turns out that linking together points where 3 rays intersect can give us one of these hexagons. And this is essentially the kind of projective geometry version. Well, not exactly, but you could think of it in a way as the kind of projective geometry version of Euclid's elegant hexagon construction. Honestly, I think one could study this picture for a very long time. So recall then that this whole construction was originally defined by where these 3 vanishing points are. And it turns out that if we move them, because Geogebra is very clever, it shifts around the whole construction as a result. Now, in projective geometry, because we're only dealing with a straight edge, the idea of having sort of set distances and angles and all the rest of it really not so important. And basically a hexagon is just something which has 6 lines. And you can see that this basic construction, the fundamental elements of it are staying the same as we move these points around, even as we flip them over. And also you can see some interesting things about sort of infinities and things like that. When you'll flip something over, you'll see a point float off through one side of the plane and reappear at the other side of the plane. Okay, so now what we're going to do is to take our hexagon projective construction and use it to make a tiling of the projective plane. Just like you can tile a Euclidean plane with regular hexagons. And the way to do it is fairly simple. We just keep extending out lines to new points from these vanishing points, and that sort of naturally produces this kind of net of hexagons. So as we continue, we see more and more of these shapes forming, and we just have to keep finding where they intersect the original lines, and then just drawing new lines from the vanishing points to join up with them. And it's really quite difficult to go wrong. You join any point you can to any vanishing points which it's not linked to already, and that'll produce more intersections, and you just carry on like that. So let's now draw in these hexagons again. And what we see is really something quite wonderful. You know how the beehive is basically like a hexagonal tiling of the plane if viewed from above? Well, we actually basically get something very similar going on here. We can just keep drawing on these hexagons, and we can just see them go off indefinitely. And because if these are regular hexagons, like in a beehive, because those opposite sides are parallel, they're like the train tracks in our perspective drawing. They're going to meet at some special point on the horizon, on the vanishing line. And that's really what we're seeing here. Okay, so now I want to show you one of the greatest, earliest, simplest, and most important contributions to projective geometry. This is Pappus's hexagon theorem, and it only involves using a straight edge, and therefore it holds in lots of different situations.
So it's easiest for me just to draw this out for you on Geogebra. So let's have a couple of lines. We'll have this first one, say red. And this second one, let's say blue. Now we're going to put some points on these lines. 3 points on each line. E, F, G on the red line. And H, I, J on the blue line. So what does Pappus's theorem say? Well, what it basically says is that if we sort of crisscross these points, I'll say it inexactly first, then I'll show you, then I'll say it exactly. But if we crisscross these points, then we're going to end up with 3 points in the middle, and they're going to lie on a straight line. That's what it says, okay? And it's actually a amazingly profound result, considering that it only involves straight lines. And I don't think the idea is particularly intuitive when one first hears of it. And it can be extended to imply so many other things about projective geometry. So let's just talk about how we're doing this here. We want to find a point which sort of, let's just say, is associated with the middle. So the way we're going to do that is to draw these diagonals from the extremities. And you see that those two cross at a particular point. So let's label that point. We shall call it K. Okay, so you can think of this as the sort of point associated with the middle, if you like. So now we want to find the point with respect to the right-hand side here, with respect to J and G. So to do that, we shall crisscross the other points. So in particular, we'll draw a line from E to I, and we'll draw a line from F to H. And we shall find where those two lines intersect and call that point L. And so finally, we want to find the third point. So basically, we can think of that as kind of associated with the left-hand side, and we find it by crisscrossing the stuff on the right. So if we draw a line from F to J, and from G to I, and then we find where those two lines intersect, we get the third and final point. And now Pappus's theorem says that the line that goes through those points goes through all 3 points. So here's where things get really remarkable. The thing is that basically what Pappus's theorem is saying is that if we have a red line and we have 3 points on it, and we have a blue line and we have 3 points on it, then they're going to generate this green line in the way I've just described. And what's remarkable is that those 3 points Okay, so the truly beautiful aspect of this, in my opinion, is just how general it is. I mean, we can alter the angles of the lines, and this result still holds. We can slide around these points and this result still holds. Even, most remarkably, if you change the order in which the lines fall in. Watch this. And this is interesting, I think, even from a sort of almost philosophical point of view. Watch point M on the black line. This point here. Watch what happens to it as I shift G closer and closer to F. It's going up, and then, oh, look, it's coming back. It's coming back from the other side. So we see things sort of go off to infinity and reappear in other places. So basically what the result says is this. If we have three collinear points, little a, little b, little c, on a red line, let's say, and we have three collinear points, big A, big B, and big C, on a blue line, and we do a certain construction, then we end up with three more collinear points. So what is the construction? Well, the construction works like this. We draw a line from A to B. We call this line we call this line A, B. It's a good name. Little a, capital B. Now we shall do something similar again. We'll take another line from little b to big A. So this line is called little a b, and this line here is called big A, little b. And now these two lines are obviously going to meet at a point. Well, I say obviously. In Euclidean geometry, parallel lines don't meet at all, but in projective geometry, we always somehow say that lines always meet somewhere. I know that sounds a bit odd, the idea of parallel lines meeting, let's say, at infinity, but it will become a lot more clear and precise as I go on with these lectures. But anyway, these two lines meet, so we can come up with some notation for the description of where these two lines meet. And we'll use the notation A, B, little a, big B, big A, little b. So it's very simple. When we're drawing a line between 2 points, we just put the name of one point after the name of the other point. That is like a description of our line. And when 2 lines meet, we just put the name of one line next to the name of another line. Simple stuff, okay? So this here is the name of this point here. Now let's carry on. We're just going to keep crisscrossing. So in a way, you can think of this point which I've just drawn. Let me overlap it in green. This green point here. You can think of this as the sort of point associated with C, if you like, because it involves crossing all the things which don't involve C. By the way, I'll just overline this just to represent that it's capital. And so now we're going to do the same kind of thing, but rather than ignoring C, we're going to ignore B, okay? So we'll draw a line from little a to big C, and we'll draw a line from little c to big A. Now here's the place where these two lines meet, and the name of that place is little c big A, because it's the line from little c to big A meeting with the line from little a to big C. Okay, so we'll draw in all the lines which crisscross and don't involve A. So that is basically just this line from little b to big C, as well as this line from little c to big B. Our theorem says that these 3 points, no matter what they're set up, they're always going to be collinear. So this is the basic notation and the theorem. So you've got it all here, and it doesn't matter. So when I say collinear, by the way, I mean that all 3 points lie in the same line. So there you go, that's Pappus' theorem.
So now let's have a look at Disargs Theorem, which is another one of the most important results in projective geometry. So here's the idea. We have a point and we have a triangle. Okay, and then we're going to have another triangle, which is, as they say, perspective to this original triangle with respect to this point A. What that basically means is that if you draw some rays out from A through each of the vertices of this triangle, then you can sort of travel along those rays and see the other triangle somewhere else. It kind of looks the same from the viewing point A, if you like. You should get the idea when I draw it. Okay, so just to recap, we have our original triangle, we have our viewing point A, and we have another triangle which is perspective to that, in the sense that these rays can be extended through the vertices. So what does the result say then? Well, what the result says is that, well, hang on, let's zoom out a bit first. One has to be careful with these kind of things, because if you don't draw them right, the places where stuff meet can be too far away to be of any practical use. Okay. There's plenty of meeting points there. Perhaps you have to zoom out a little bit more. Okay, so there's an extra point of intersection. And now the big result is that these 3 points here actually lie on a straight line. It's such a special straight line, I think we should give it a new colour, maybe green. Okay, so this is Disargs Theorem. It states that if you got one triangle perspective to another, and then you extend out these lines, then they're going to, if you look at the places where those lines intersect outside the triangle, they're going to form a kind of they're going to be collinear. Okay? There are more complicated ways to say this result, but just watch. As we shift things around, it always remains the same. It doesn't matter if the triangle is inside or outside, or whatever. We can even shift around the parts of the triangle, but the result always holds. Very interesting. Okay, so I've just zoomed in a bit on this picture of the hexagram. This picture of the hexagon. And I want to show an application of Disargs Theorem. So you see I've highlighted a couple of these triangles here. This yellow one here. And this orange one here. And these are both perspective to each other with respect to this point D. So according to Disargs Theorem then, we ought to be able to figure out three collinear points which sort of get generated by these triangles. And we can do that. So let's just find a line generated by one of the triangles. So here's one. This line generates this side of the triangle. And we extend it, it goes up here. Now, if we find another line generated by a triangle, let's say this one here, we extend it, it goes up here. And so we get this point here. Now let's do something similar again. We'll use this line here now, generated by this yellow triangle, and that goes through here. And we'll use this line here, generated by this orange triangle, and that goes through this point here. So we get this point here, and you can probably guess the third part of what's going to happen. If we look at this side of the triangle, we have this line here, which is this line here. Line, sorry. And finally then, if we have this bottom line of this orange triangle, that's this red line here, which is this red line here. And so we also get this point here. So in this case, according to Descargues' theorem, we get these three collinear points by extending the sides of our perspective triangles, and they all fall upon a line, and it turns out that that line is actually the vanishing line.